So there are two more videos yet in chapter 15 on buffers, and then, like I said, this is a tough chapter. That is titration curves and how indicators and how they work. So typically what we do is we do a lab for this, but we don't have that option, so we're going to go with just me explaining how titrations work. Usually what you're using a titration means that you are adding a strong base to a weak acid, and you're normally doing this in order to determine the molarity of the weak acid. Okay, or you can titrate a strong acid to a weak base, and you're trying to find the molarity of the weak base. I mean, there are other uses, but I'm just saying that's one of the things that you use titration for. Titration just means you're adding a volume of a strong acid or a strong base either to a weak acid or to a weak base. Now, you have to know where you are along the titration curve in order to solve the problem. So we are going to begin by doing a strong base, weak acid titration. And I'm going to do the same acid as in the book, but different numbers. I'm going to do acetic acid, and I'm going to start with 50 milliliters of a 0.1 molar solution of acetic acid. I'm going to titrate with my strong base, and the strong base that I'm going to use is sodium hydroxide, and the concentration I'm going to use is let's use a different concentration since they're. Let's go with 0.2 molar. No, let's stick with 0.1 molar. It'll be good to see a couple ways to do the same problem. And we're going to go with the same concentration over here. Now, you don't have to have the same concentration. We could titrate with a different concentration of base, and sometimes you do. Sometimes you go with the stronger concentration of the base so that your titration goes quicker. Okay? So a titration curve, on the y-axis you have pH, and on the x-axis you have the volume of base that you add. So in this case our base is sodium hydroxide. And when we begin, it means that you just have no volume of base added. So this would be 0, and then we can make some marks along the way of like 10, 20, 30, 40 or something like that. Let's see. Yeah, let's just do 25, 50, 75, 100. Okay? And then your pH scale runs from 0 to, well, typically it runs from 1 to 14, but I can do a better job at doing this. All right. So when you begin, you're going to have an acidic pH. Why? Because you have a weak base. A weak acid in water. Okay? I'm going to call this point A. So before you even add any base to your water solution, you can calculate the pH. How do you do that? So at point A, all you have is the acetic acid in water. So the way you solve for your pH is just like we did in chapter 14. You're going to do an ice table. Okay? We don't have a buffer. This is just acid and water at point A. So start with your initial concentration. Ice tables are always in molarity. 0 of this, 0 of this, plus, 0.1 minus x, x, and x. And then we look up the Ka of acetic acid, which is 1.8 times 10 to the negative fifth. And that's what we have. This x is too small. And so then when we solve for x, I get 0.134, whoops, nope, 0.00134 molar of H plus, and then my pH is going to be the negative log of that. So my pH is going to be 2.87. Okay? So when I just have the acid and water and nothing else, my pH is going to be 2.87. So when I start, my pH will be 2.87. Now, what's going to happen when I start to add my strong base? So we're going to add sodium hydroxide to the acetic acid. Well, what do you think is going to happen to my pH if I start adding a base? Well, the pH is going to go up. So as you watch, the pH kind of goes up like this. Okay? This is section B. So everything in blue here is section B. Okay? What's going on in section B? Why isn't it a straight line? Well, let's just do an example here. Let's pick, let's say we add 20 milliliters. No, let's make it a funky number. Let's say 22 milliliters of sodium hydroxide. And we began with 50 milliliters of the acetic acid. Now, a before and after table has to be in moles. So my concentration of this is 0.11 molar. So the number of moles I begin with is 0.0022 moles. And this is a 0.1 molar concentration, so I start with 0.00500 moles. These two react, and I'll end up with the salt plus water. Okay? Well, what do I have more of? Do I have more hydroxide or more acetic acid? So all of this is going to react, and I will end up with 0.0028 moles, which means I'll end up with 0.0022 moles of that, and I really don't care about the water. Okay, the amount of the moles of water being generated is too small for us to care about. Okay. So I've created a salt. Well, what do you have when you have a weak acid and a salt? You have yourself a buffer. So in section B, it's buffered. It's a buffered system. At point A, it's not a buffer, but the whole blue section is a buffer. And if it's a buffer, we can use the Henderson-Hasselbalch equation. We just have to convert this stuff into molarity. You could work out an ice table if you want, but that'll take longer. It's much quicker if we use the Henderson-Hasselbalch equation. So I have 22 milliliters plus 50 milliliters. So that means my total volume is now and my molarity oops, wrote that down in the wrong spot. All right, so those are our molarities, and we can use the Henderson-Hasselbalch equation. Okay, to plug into that. So the pKa is going to be the negative log of the Ka, which is 1.8 times 10 to the negative fifth. So my pKa is 4.74, and I'm going to add to that the log of the concentration of 0.0306 over 0.0399. Whoops, sorry, I'm combining problems here. That's the pKa. The pH is going to be equal to my pKa plus the log of 0.0306 over 0.0399. All right, now let's plug it in. All right, so when we add 22 milliliters of a 0.1 molar concentration of a base, that's going to be our pH. Okay. Now, once again, you're more than welcome to work out an ice table, but using the Henderson-Hasselbalch equation is a heck of a lot easier. So, at right about there, my pH is 4.62. Okay. Now, we use the Henderson-Hasselbalch equation in this entire blue region. Okay. In the red region, remember you have to use an ice table. I mean at point A. That's just at the beginning. You've got to use yourself an ice table. Okay? Now when we get to this point right here, that's a really special point. that's point C. And point C is the equivalence point. And that's a very special point. And for those of you who are mathematically oriented, the equivalence point is the inflection point on your curve where your slope changes from negative to positive. Okay? So at point C, the way we define it is the moles of strong base equal the moles of weak acid. Okay? Drill that into your head. Get that correct. It's when the moles of your strong base is equal to the moles of your weak acid. So my weak acid is this. I've got 50 mils of a 0.1 molar solution. So that means I have 0.00500 moles of weak acid. So how many moles of base must I have to be at the equivalence point? Okay? When you are at the equivalence point, the moles of base and the moles of acid, the moles of strong base and the moles of weak acid are equal. So I know that this number must be this. Okay? Has to be. All right? Now, because my concentration is this, they did that on purpose, and I did that on purpose to make it easy for you to figure out the milliliters, right? Because how many milliliters would I need to give me that? Well, I would need 50. But you don't have to have the same concentration. If we made the problem trickier, we could say, well, what if we had a 0.2 molar solution of base? Well, then how many milliliters would you need? You would only need 25 mils, right? So, but to make the problem easier, and they usually do this on the AP as well, test, is they give you the same concentration so that you can, in your head, realize, oh, well, then the volumes have to be the same. So what will happen here is like before, they're going to react, and then afterwards, because they are equal, you'll have none of this and none of this, and 0.005 moles of the salt. Okay? And again, we don't care about the water. Okay? So now, at point C, this becomes a problem like we did in chapter 14. All we have is salt. That's all we have in there is a salt, nothing else. All the acid has reacted. There is no more acid. All the base reacted. There is no more base. All you have is a salt in water. And as we remember from chapter 14, salts will either make your solution acidic, basic, or neutral. Now, this salt is going to make our solution basic because, actually, let's do this. Here's my salt. Okay? We don't care about the sodium. Okay? Boop, there. Because the salt's going to break apart. The sodium doesn't do anything. It's just floating around in solution. But the conjugate base, as you know, is going to react with the water to do this and produce a base. So at the equivalence point, my pH should be basic. Why? Because I'm producing OH. And now let's prove it. This has to be an ice table. Okay, so point C and point A both have to be ice tables. How many moles do I have? This many moles. But remember, ice tables have to be a molarity. So how much volume do I have? Well, let's go back and look. We've got this much of this and this much of this, so 50 plus 50 is 100 mils. So we're going to divide by 100 milliliters, and so my molarity is 0.0500 molar. All right? 0 of this, 0 of this, shift right, shift right, shift right, 0.0500 molar minus x, x, x. But we are producing a base, so this is a Kb problem. So I'm going to have to find my Kb. And my Ka is 1.8 times 10 to the negative fifth. So my Kb all right. And then I'm able to go ahead and do my Kb problem. So I get 5.56 times 10 to the negative 10th is equal to x squared over 0.500 minus x. That one's too small. So we solve for x. And I get 5.27 times 10 to the negative 6th. Don't forget, this is the concentration of OH, right? That's why we label everything. So then my POH is 5.27. Therefore, my pH is equal to 8.72. Okay? So, like I said, this salt should be making my solution basic. And if I go all the way back, there's my pH, 8.72. All right? At point C, you got to use an ice table. And like I said before, that is the point of inflection where your slope changes. So for the rest of the problem, your curve is going to do that. That's section D. And in section D, it gets easier. All you have to do is calculate the pH of a strong base. So all of my acid has reacted. There is no more acid left. So if we add more base, there is nothing left for the sodium hydroxide to react with. So let's say I add 60 milliliters of base, okay? Well, we know from up here the first 50 mils will react, and that's why it's important to know the equivalence point. So we already know that 50 mils of it will react. I suppose we could do a before and after table. That would be probably the best way to explain it, but you could probably reason it out in your head. So I got 60 mils at 0.1 molar. My acetic acid, 50 mils at 0.1 molar. So I've got beforehand 0.00600 moles of my base, and I got 0.00500 moles of my acid. They will react. Afterwards, I will have that much left, and I will have no acid left. Okay? What is this going to generate? Okay? So beforehand, I have 0 of this, 0 of this, and then I will generate 0.005 moles of this. Okay? Now, if you go back in your problem sets from chapter 14, I had you do this problem. What is left is you have a strong base and you have a weak base. The salt is going to produce a weak base. So if you have a strong base and you have a weak base, the weak base doesn't matter because it doesn't break apart 100%. The strong base does. So it's not important at all that we've got some of that salt floating around, unless for some reason the problem asks you to calculate its concentration. But we don't have to take into account the weak base at all when calculating the pH. All we care about is the strong base. So that makes our problem a heck of a lot simpler. So I know I've got 0.1 mole of sodium hydroxide that did not react. We're going to divide by the volume. Well, 60 plus 50, 0.110 liters. So my molarity is 0.909 molar of sodium hydroxide. Well, as you know, that's going to break apart. Give me my hydroxide. It'll give me that much. We don't care about the sodium, but if you did, well, actually, no, that's not the concentration. Let's just not care about the sodium because we don't. Okay? So the pOH is going to be negative log 0.909. So my pOH will be and therefore my pH is going to be 13.95. So when I add 60 mils of hydroxide, whoops, so 60 mils, or about 3.95. I didn't quite do it perfectly, but the equivalence point, as you can see here, is at 50 mils. Okay, didn't quite do it perfectly. Okay. All right, so in this section, like I said, you will use pOH equals negative log concentration of OH because you now have a strong base. Okay, so no ice table is involved. So at the equivalence point, my pH is basic. All right, the point of inflection is basic. All right, so the last point I want to make is oh boy. Well, actually, there's a couple points I want to make. So the equivalence point is 50 mils. Okay, that was the equivalence point. There's another very special point, and that is halfway to the equivalence point. So if the equivalence point is 50, halfway would be 25. Okay? So why do we care about halfway to the equivalence point? color are we using there? Okay, section B, we need to use blue. So halfway to the equivalence point, would mean that your moles of strong base are half of your moles of weak acid. Well, why do we care about that? Well, let's do a before and after table here. So we got sodium hydroxide, and we've got our weak acid, 50 mils, 0.1 molar. So beforehand, that's the number of moles of weak acid. So that means halfway, I would have half the number of moles of my strong base, okay? Half the number of moles. I'm not even going to put the volume and stuff up here because I don't even want you to confuse the two. What you really want to remember is that halfway to the equivalence point, the moles of strong base are half the moles of the weak acid. Here is where people get confused. Okay? Afterwards, all of my base will have reacted. I'll have this many moles of my weak acid. But how many moles of salt did I generate? Notice that these are equal. Okay? So I can't underscore the importance of understanding this, okay? And so I'm going to take up an entire page. I'm going to go back here. This is the weak acid. This is the conjugate base, okay? Conjugate base, conjugate base, conjugate base. So at the equivalence point, or at halfway to the equivalence point, the moles of weak acid equal the moles of conjugate base. Okay? At halfway to the equivalence point, the moles of weak acid equal the moles of conjugate base. It's not that the moles of the strong base is equal to the moles of weak acid. No. Okay? That is not the case. At halfway to the equivalence point, the moles of your strong base is half of the moles of your weak acid. But the moles of the weak acid and the conjugate base are equal. Don't confuse that ever, okay? Because something very special then happens. Technically, I don't need to know the molarity when I'm at halfway to the equivalence point, but I'm going to calculate it anyhow. So, let's see here. let's take that, divide it by my volume, which would be 0.075, divided by 0.075, because I'm going to add 25 mils of this. So that means the molarity is 0.333 molar, 0.333 molar. So what happens here? What happens at halfway to the equivalence point? At halfway to the equivalence point, you will always be taking the log of 1. Always. And the log of 1 is 0. So at halfway to the equivalence point, the pH is equal to the pKa. Okay? So this is typically how you find the Ka of a substance. What you do, and this is what we would do, like if we were to do the lab, you would make your graph. You would do your titration and make your graph. You would find the point of inflection. Then you would find out, okay, what was my volume there? Well, let's say my volume was 60 milliliters. Well, then I know that at 30 mils would be the halfway point. So this would be the equivalence point. That would be halfway. Well, the pH at halfway is equal to the pKa. So what you would do is you would measure the pH and then calculate the Ka. That's how they find the Kas. Okay? Now, the problem that we did, we know the pKa and we solve for the pH. But when you're in the lab, what you do is you graph, find the equivalence point, find halfway to the equivalence point, measure the pH at halfway to the equivalence point, and then calculate your pKa. And that's how they find Kas. And unfortunately, we can't do that lab. Maybe I can find an online version, but that's what we were doing. Okay, one last thing. I know this is a long lecture, but when you titrate a weak acid with a strong base, the equivalence point is always basic, meaning that the titration curve will always have the inflection point in the basic region. Okay? If you titrate if we do the opposite, and we do a weak base with strong acid, it reverses. Think about it. If we're starting with a weak base, our pH would have to start basic, and the inflection point would then be in the acidic region. And then last but not least, what would happen if you titrated a strong base plus a strong acid? If you titrate a strong base and a strong acid, then what would happen at the equivalence point? The equivalence point would be a pH of 7. So sometimes they do this in a problem. They'll say like, okay, what's the equivalence point when you react sodium hydroxide with HCl? You know what the equivalence point is. The equivalence point will have a pH of 7 because it's a strong base reacting with a strong acid. Okay? I suppose I feel obligated to just draw out what happens if it's a diprotic acid. Suppose you did carbonic acid. It's got 2 protons, and you titrated it with a strong base. Well, same thing happens, that, like I just said. If you titrate a weak acid with a strong base, the equivalence point is always in the basic region. But because there are 2 protons, you go through the curve twice. There'll be a second inflection point. The first equivalence point is for the first hydrogen coming off. The second equivalence point is for the second hydrogen coming off. Okay? So, yeah, this is a lot. That's why it's unfortunate that you're having to learn this thing virtually. There's only one more lecture, and it'll be much shorter. It'll be about 15 minutes on indicators and how they tie into titration curves. But good luck. If you have questions, just email me.